Hi, everyone. Before I get into my first topic, what I just want to say is that watch how I give this presentation. I have a experience with giving PowerPoint presentations and how presentations should be done in general. I've taken like classes and had some club experience and stuff like that. So I want you to notice this. Primarily, what I want you to notice is many people have lots of words on PowerPoint, but it really shouldn't be done like that. So I want you to see, I personally feel like this presentation has too many words, but it doesn't have that much. But try to do that. It's going to be something really important when you take classes in college and you're going to be presenting all the time. So it's important to know how to present a PowerPoint effectively. And I'm going to be trying to do that as best I can. Of course, I'm not an expert, but I do think I am pretty good. So as you're also learning, also see how I'm presenting the material for this one and the next one. All right, so I'm going to be talking about special relativity and time dilation. So this is a theory that was discovered by Albert Einstein. And what he discovered was that you can actually slow down time and speed up time by doing something. And it sounds like kind of sci-fi and wacky, but it's actually very real. And it's something that people can experience every day. It might be small experiences, but it's just something we all experience. And you might have had some experience with this or thought about it if you've read sci-fi books. Many times it's very popular in sci-fi books, for example, in Interstellar, where he becomes like old and then he goes to a planet and he comes back and everybody's old. Or in Ender's Game, where they're meeting this person, he's supposed to be like 800 years old, but for some reason he's not dead. And this is something that people in jet planes or astronauts experience a lot of, where they're supposed to be older, but for some reason they're not as old. And these are all very real things. This isn't fake. This is all real. So I'm going to be explaining how is this possible? How can you slow down time and things like that? And what is this whole special relativity thing? And more for special relativity, I'm going to be talking about time elongation. So before I go into that, there's two rules that we want to look at. Rule number one, the relativity principle. The laws of motion are the same in every inertial frame of reference. I'll talk more what that means. And number two, the constancy of the speed of light. The speed of light is the same independent of speed of the source of the observer. So that means that everyone observes the speed of light going at the same rate as everyone else. Okay, and speed of the light is the fastest thing in the universe. Okay, nothing can go faster than the speed of light. It's the fastest thing. So the relativity principle. So physics works exactly the same way no matter your frame of reference. So what that means, so if we're looking at this guy here, he's seeing this train go by at 15 meters per second, and this guy inside the train is walking at 1.2 meters per second. So what's happening is this guy on the ground is going to be seeing this person move at 16.2 meters per second because he's moving with the train. However, this guy over here, and if he was looking at the person over here, he wouldn't be able to tell if if he wasn't hearing sounds or if he wasn't looking at the background, if he was the one moving at 16.2 meters per second, or if the person on the ground is moving at 16.2 meters per second. So you don't know who's moving or who's not moving. And you might have experienced it if you've ever been on the bus or the train and you're not sure is it moving outside or is the train moving and you really don't know. And there's no experiment that you could do to figure out which one is moving or not moving. And nowadays, we're trained by our ears and what's going on in the background to be able to say, okay, they're probably the one moving or we're probably the one moving. But there's no physical experiment that you can do to figure out who's moving. It's just like on Earth, we're moving at around 1,000 miles an hour, but there's no experiment that we can do that can actually physically show that. Okay, so this is the first principle that we have to know, that no matter how fast you're moving or how things are interacting, that it's impossible to know who's moving and who's not moving. The second principle is the constancy of the speed of light. And so the speed of light is the fastest thing in the universe. It moves at around 300 million meters per second. There's nothing faster than the speed of light. And I just want to explain what that means for a second. So if I move my hand like this, depending how far you are from the screen, it's going to take a little bit longer for you to notice my hand move. So if you're in the back of the room, it's going to take slightly longer for you to notice that my hand moved. But if you're right in front of the screen, and if I move my hand like this, it's going to you're going to notice that my hand moved slightly quicker. And the reason it's so slight is because light moves at 300 million meters per second. So even though you're in the back of the room, it seems like you're seeing it instantaneously. But it takes time for things to travel. So when I move my arm, if you see a ball move or something like that, it takes time for that motion to come to you and to understand that something is moving or something is happening. That's also why this is a bit of a tangent, but we call it the observable universe, because there are things changing in the universe, but until the speed of light reaches our point, that's all we know of that thing. So there are things outside of the universe where the speed of light has never caught up to us, and so we cannot see. It's impossible to see. But just know the speed of light is extremely fast. That's why it seems like everything is instantaneous. But if you're in the back of the room, it takes longer to see something happen than if you're closer to the object. Okay, so speed of light. So now I want to talk about this constancy of speed of light. So we see this archer here in this first picture. Archer B shoots an arrow at 200 kilometers an hour. And then we see this person in the train who's also an archer. And the person in the train is going 100 kilometers an hour and he shoots an arrow at 200 kilometers an hour. What we know is Archer B, if we look at the arrow, it's going to look like it's going 200 kilometers an hour. However, what we know, if this person shoots it in the train, this arrow is now going to look like it's going 300 kilometers an hour, because we know we have to add the 200 with the 100. But let's now look at this bottom one over here. We see that this person has a laser gun and this person has a laser gun, so there's like shooting light. So when this person on the ground shoots light, we see it's going to be moving at 300 million meters per second. However, now let's say this train over here is moving really, really fast. It's moving really, really fast and shoots this light beam. What we're going to notice is this light beam is still moving 300 million meters per second, because nothing can be moving faster than the speed of light. So even if you're moving faster and you shoot a light beam, it still looks like it's going 300 million meters per second, because nothing can go faster than the speed of light. So that becomes kind of weird now. So now you have to start thinking, okay, if nothing can go faster than the speed of light, that means these two people, A and B, have to be experiencing something different. So this person can see speed of light going 300 million meters per second. It travels this distance and takes a certain amount of time. However, this person, when he shoots his beam of light, he's noticing that the beam of light is also traveling at 300 million meters per second, and it's going this same distance, but something has to be different, because if they're both seeing light go at 300 million meters per second and the distance is the same, there has to be something different that they both experience. So if the speed of light is the same for both of them and the distance the light travels is the same for both of them, that means something has to be different, and that's time. And I'm going to be talking about how time is going to be different and how that changes. So if that was confusing, I'm going to be explaining it again in another screen. So when we look at this, let's call this like a little clock. And this is a light beam in the clock. Again, speed is equal to distance over time. And let's just say the time it takes for this light beam to go from here and back takes 1 second. This isn't proportional at all. This, of course, would be a lot bigger. So this beam is going 300 million meters per second. And the distance it travels from here to back takes 1 second. Okay? However, with this light beam, let's now take this light beam and put it on a rocket ship. So when this light beam is going, this person is moving, we're going to see this light beam isn't going to be moving up and down anymore if we're just looking at it head on. It's going to be moving at an angle like this. It's going to go up, down, diagonally like this. So we know that the perfect person inside is just going to be seeing it go up and down regularly. But if somebody's looking at this, we're going to see that the person looking at this is going to go diagonal like that. And what we notice is the person inside looking at it we'll see the distance it travels from here to here will be this d. However, the person looking at it from the outside is going to notice that the distance it travels is from here to here, meaning the distance is bigger. So what we're going to notice, they're both going to see the speed of light going to be exactly the same. However, what they're going to see is the distance it travels is going to be a lot more. But in order for the speed of light to be exactly the same, if this distance is more, that means the time has to be more in order for the speed of light to equal the same thing. And what that means is that the person inside the plane who's only seeing the beam travel like this is experiencing time more slowly than the person that's not moving. I know that's a bit complicated, so I'm going to kind of go through that one more time in another picture. So what we see here is this person in the jet plane. The person in the jet plane is seeing the beam go up and down like this, and it takes 1 second. However, the person who's not moving sees the beam go all the way here and all the way there, so it travels a lot longer. However, the speed is the same. The distance that light travels is different. So in order for speed equals distance over time, and the distance is a lot longer, and the speed is still the same, that means time also has to be longer in order for the speed to be exactly the same. So that means this person is going to be experiencing time a lot faster than this person over here. And what this means is the faster you go, you experience time slower. And this is physically true. We don't notice it because you have to be going extremely fast in order to experience this. So you have to be going extremely fast to experience anything significant. However, this is what's happening in those movies and those sci-fi books and to jet airplanes. They had an experiment where a person in a jet airplane flew really far distance and they brought this atomic clock with them. And when they landed, they noticed that their atomic clock was behind the person on Earth who did not travel. And so it shows that the faster you're going, time is slower for you, which is extremely strange. And there's a lot of strange things that actually happens. Though the faster and faster and faster you go, the slower time is for you. Okay, it's kind of interesting. And that's why if somebody goes to one planet really fast and comes back really fast, they're not going to be experiencing the same time delay as someone else. So when you come back, everyone might be old while you're young, but you have to be going extremely fast to experience something like that. But this is part of special relativity, the time elongation. There's other things like length elongation, increase of mass, and this is where the famous equation E equals mc squared comes from. I'm not going to be talking about this, but there's a lot of cool things that happen when you start to travel really fast, and it gets kind of crazy, but it's all real. It's all been proven and everything like that. All right, I hope you guys learned something, and I hope you guys enjoyed this, and I look forward to the projects that you guys are creating. All right, good luck.